Welcome to solverfy.
For this problem, they are asking us to find how many molecules of methane are in a container that is part methane, part argon, and part helium at certain conditions. So they tell us that the mole fraction of argon, abbreviated AR, is equal to 0.35, and they tell us that the mole fraction of helium is equal to 0.25. They tell us that the volume of the container is equal to 6 liters, and they tell us that the pressure is equal to 1.75 atmospheres. They also tell us that the temperature is equal to 45 degrees Celsius. I'm just going to turn this into Kelvin by adding 273 Kelvin. So our temperature is 318 Kelvin. So we know that the partial pressure of a gas is equal to its mole fraction times the total number or the total pressure of the container. So this is the partial pressure of our gas. This is its mole fraction. And this is the total pressure. All right, so to get our mole fraction of methane, CH4, we know that the mole fraction has to equal 1 for all parts of the mixture to equal the total pressure. So we know that if we take 1 minus the mole fractions of argon and methane, so 0.35 plus 0.25, we're going to get the mole fraction for methane. So this is going to be 0.40 for the mole fraction of methane. So to get the partial pressure of methane, so partial pressure of methane, we're going to take the mole fraction of methane and we're going to times that by the total pressure. So we know that our partial pressure is going to be our mole fraction, so 0.0 or 0.40 times the total pressure, which they tell us is 1.75 atmospheres. So we know that the partial pressure for methane is going to be 0.70 atmospheres. All right, so now that we have the partial pressure for methane, we can find the molecules. But before we find the molecules, we need to find how many moles of methane we have. So we're going to be using PV is equal to nRT. We want to find out how many moles we have, so we're just going to rearrange it. All right, so now our moles is going to equal our partial pressure for methane, so 0.70 atmospheres. We're going to times that by the volume of the container, which is 6 liters. We're going to divide this by the R value. I'm just going to use R is equal to 0.0821 liters atmosphere per mole Kelvin. And we're going to times that by the temperature, which is 318 Kelvin. So our moles is going to be 0.161 moles of methane. All right, so now to get the molecules of methane, we're just going to take our moles, so 0.161 moles, and we're just going to times that by Avogadro's number, which helps us get moles into molecules. So Avogadro's number is 6.023 times 10 to the 23rd molecules per mole. So when we calculate this out, our molecules of methane is going to be 9.7 times 10 to the 22nd molecules of our methane. All right, and this is how we solve this problem.